So our next speaker is Daniel Garijo. He is a computer scientist in the Artificial Intelligence Division. Somewhere behind me.
Hello. Thank you. Can you hear me? Yeah, all right. So today I'm going to be talking about the challenges for reusable scientific software. And I would like to start my talk with by mentioning a paper that was presented, a survey rather, that was presented by Nature in 2016, where they basically asked more than 1,500 people, research scientists from different domains, ranging from chemistry, biology, physics, engineering, medicine, etc., whether they thought there was a reproducibility crisis. And well, more than 50% answered that yes, they thought there was a significant crisis. An additional almost 40% thought that there was at least a slight crisis. But what I was interested more in this paper is that they also did a question, which was whether at some point in their lifetime, someone had failed to reproduce an experiment made by a colleague or an experiment made by their own in the past. And what is shocking is that at least more than 40% in most of the domains acknowledge that they failed at least once to reproduce an experiment by their own group or by themselves. So there are different reasons for this, and they argue that, well, sometimes there is a little of cherry picking of results, that there is not a very good usage of statistics, or they also said that there is sometimes a problem of the experimental that the experimental design is not very robust. But well, in our domain, which is computational sciences, I wanted to focus a little bit more on our domain, which is computational sciences, right? And in our domain, well, you see that a scientific publication has like three main pillars, which is for reproducibility, which is the availability of the scientific data, which is the data that we talk about in our experimentation, the scientific software, which are all, even those ancillary steps that we use to transform the data for transforming and creating additional scientific data, and finally the scientific methods, which are, as Eva was mentioning in her talk, how we compose the different software pieces to actually achieve the results that we discuss in our publication. And in here, we have seen a lot of progress since 2016 and even before, right? Now we see that open sciences is more and more common, and there are platforms such as Figshare, Zenodo, and Dryad and Dataverse that actually not only allow you to share this in your papers, that also allow you to get a citation for your data, and that's great. And for scientific software, we see more and more papers where now people add links to their repositories. And some of them have even links to Zenodo, where you can even get a citation for your software, which is excellent. And finally, we get, for the scientific methods, journals are also getting more and more interested. Now there are journals like Method X and PLOS ONE, which accept computational scientific methods as part of research collaborations. And we also see open platforms such as Wings and Pegasus that allow you to define scientific workflows, computational methods a little bit more formally for enhancing reproducibility. In this talk, I'm going to be focusing a little more on scientific software. If I can pass the next slide, which apparently doesn't work very well, because scientific software is basically the main glue between data and methods. But there are challenges. I mean, scientific software is not without challenges. And you have to also separate the perspective of these challenges depending on what you want to do. If you are a software user who wants to understand the work made by others, or a software designer that is someone who is publishing a paper and wants their software to be as widely adopted as possible. So as a software user, you face different challenges. The first one is that you want to understand what your software is doing, right? And sometimes the software that you want to use, the software component that you want to use, not only has one method, it has multiple methods. So you have to spend a lot of time figuring out how should you use it. Then you also need to to know how to transform the data for the particular software that you want to use, which, well, in theory, if you just look at the notion of reproducibility, it should be just obtaining the same results. But in practice, we don't only want to obtain the same results that were mentioned in a previous paper. We just want to adapt the particular software component to use it with our own data. Similarly, we want to interpret the results that the software component is creating so we can actually use them, right? And then you also need to figure out small things that may need a little time as well, such as how to invoke a software component, which is not always trivial, and how to configure it appropriately with, for example, the different hyperparameters, right? In terms of machine learning, I know many colleagues that were frustrated because the authors were giving the particular software pointer in their papers, but they didn't give the hyperparameters, and therefore they were really struggling on getting very similar results with what they claimed. From a software designer point of view, this is kind of related to what Eva was telling us, right? Because the first thing that you have to figure out is how to capture the dependencies and installation instructions to make sure that someone else can use it. Someone else can use your piece of software. And you also need how to encapsulate your software so it can be used with other data. You cannot imagine the amount of times that I've been trying to use software by other person, and it turns out that there are hard-coded paths that make it very, very difficult to use with different data, right? And, well, this needs an extra effort that needs to put on whenever you are trying to make your piece of software components share with other people. Finally, well, you also need to know how to describe your software, and many people don't know how to do this. So most of the details of what they are doing are in their heads, but it's very difficult to communicate this because they think most of these details are trivial. And finally, another problem that we are facing is that you don't know when you're done. You say, OK, I'm going to put this out there, but I hope that someone else can use it. And the way of testing this out is usually just going around and asking a colleague. So I'm going to go briefly on how we have or attempts to try to address these challenges. And the first one, what we did is, OK, well, if we want to actually try and explain what the software does and how to document it, let's try and go to the source. We went to different communities of scientists, starting with the earth sciences, and we tried to talk to them on how to translate the software metadata that we thought was necessary in their own language. So how we did this in terms of questions and answers, and we presented them forms that they filled, and we got very rich metadata entries that were filled, and so we will be able to share them, and we would be able to start structuring them a little. And this was done in a crowdsourced manner, so different communities would be the ones responsible for filling the knowledge about their own software in their own community. And what we follow up with that is that we said, OK, well, let's try to add a little bit more structure into this initial unstructured knowledge, right? So we started creating knowledge graphs with machine-readable software metadata, adding very thorough explanations about how the inputs of a particular software component were required, well, not only the inputs, but also the variables that were included in these inputs and outputs, how to get information about the units that these variables were in, what was the information about the containers, and so on and so forth. And this is part of the main project, the model integration project. Eva was also mentioning in some of her slides. However, well, as I haven't been worked very hard in that project, I know that also gathering all this metadata sometimes takes a lot of time. So part of the work that we started doing last summer was trying to get this metadata a little bit more in a semi-automatically or completely automated manner. So as part of the REU program, we had one student that basically the idea that he worked on is that you would start with a software repository that would go through a software metadata extraction framework and would automatically extract from the documentation, because some of this metadata already exists. You just have to go through manuals and get the different metadata fields. And we started by getting 4 very simple metadata fields: the description, installation instructions, invocation, and citation, right? Which when you are actually analyzing any particular software component, these are the first things that you may worry about. And actually, his results were pretty OK to start with, because he created a hand-created corpus over 70 repositories on GitHub, and he trained for binary classifiers, and he got pretty good initial results. We're still analyzing them. And finally, what we are also working on is from the designing point of view, which is on encapsulating and testing software components. The idea here is that a software designer would come with their own software piece, and with the help of assistant and guidelines, would create machine-readable component specifications that would help us create automatically tests for testing whether the software is OK or not, and creating portable components. The good thing is that with these machine-readable descriptions, at the same time, we can create entries in software metadata registries, and therefore the software can be found by others and can be completed by others as well. And then executed in execution engines such as Wings and Pegasus. So, and this is my last slide. I think that the improving better descriptions of scientific software is a critical asset for reproducible computational experiments, and also for addressing a very, very important part of reproducibility. I think that we really need to improve the reusability and understanding of scientific software, so we increase the adoption of the scientific products that we are doing, that we can create better comparison of similar computational methods and actually help explain better how results are created, because most of the time, at least in our domain, they are created from software. And finally, I also think that there is a huge opportunity for intelligent systems to create a difference here, because they can help us interpreting existing software and how to use it. And also, this may have impact in other domains, such as cybersecurity. You want to know whether a particular software may be a threat or not. Intelligent systems can also help prepare and visualizing data, help describing software component, encapsulating, and finally composing different software pieces together to actually achieve what we want to achieve in a more rapid manner. And I wanted to finish just by reminding about the rest of the group, the Knowledge Capture and Discovery group, led by Yolanda Gill. And I think we have a poster session, so I'll finish with this. Thank you very much.
Hi, I love the hardness of the problem you're trying to tackle, was trying to get reusability into software and make it understandable for developers to pick up is really, really difficult for end users. So the metadata extraction into something that's easily understandable in a sort of a common format, I think, is a fantastic idea. But one of the things that I think is missing, or at least in your slides, is being able to pull out cookbook, tutorial, example, usage type scenarios, because that's actually, I think the easiest thing for people to pick up on. Do you have any progress in that area at all?
Well, I think almost in the last slide, I also had some sort of guidelines and assistance to actually help this, and that would go in that direction. Actually, I didn't mention it, but as part of the OntoSoft project, we also developed a set of tutorials and good practices for people, and basically a cookbook that would tell you how to share your scientific software in 5 minutes or in 10 minutes, depending on the amount of time that you had. And there is we had everything in a website called the scientificpaperofthefuture.org. And if you go there, you have hours of materials on how to do this, depending on the time that you want to spend on. But I completely agree, and we have spent some time on that. It's just that in 10 minutes, I didn't have a lot of time to talk about that. I apologize. All right.
So in your initial study that you were showing, where you pulled data from GitHub and annotated, did you focus on a specific scientific domain, or did you just go broadly?
We didn't focus in an initial scientific domain. Actually, Alan, which is the RAU student who started doing this, we just said that it had to be scientific software, so that had people that cared also about citation, and it was more or less research software. But we didn't want to choose a domain. The initial approach was just, let's try to do it, and let's see what results do we get. Initially, we're good, but well, we need to further improve on that. All right, thank you.
Thanks.
Oh, no problem.